Alright, so last time I explained how flat bundles are related to representations of the fundamental group of the manifold. And now I want to state an interesting result in this connection by Milnor about the existence of flat connections. Milnor in the 1950 something, 7 or 4, I don't remember exactly. So the situation is the following: let M be a surface, and in fact it should be a surface of higher genus, a hyperbolic surface. So let M be a compact, connected, oriented two-manifold surface of genus at least 2. So that's the underlying manifold, and we look at bundles over this manifold. So let F be a bundle. It's an oriented, two-dimensional real vector bundle. So I could write let F be an orvect 2 bundle on the manifold M. The two-dimensional or rank 2 bundle of oriented vector spaces. And then the statement is, then there exists a flat connection on that bundle. So connection with the vanishing curvature on F, if and only if the Euler characteristic of that bundle, so this is an oriented vector bundle, so it has an Euler class. So let's look at the Euler class of that thing. So that's a class of degree 2, because it's of rank 2. So degree 2, so the 2 is exactly the dimension of the manifold. So we can evaluate this class on the manifold, or integrate representing form over the manifold. This gives us some number, and this number has to be less than a genus. So that's the result. And that's quite remarkable, because it means that in most cases this flat connection on bundle F cannot be used to represent the Euler class. Right? Because if I have a connection representing to which if we take the curvature, apply the Pfaffian to it, then this gives us a representative of the Euler class. But if the connection is flat, then the curvature vanishes, and so the representative vanishes. But if we find a bundle such that this number, so that is not 0, but still less than G, then the theorem says you have a bundle with a non-trivial Euler class, but a connection with vanishing curvature. Okay, so let's keep this. So unless this Euler class is actually 0, which is in fact equivalent to the bundle being trivial in this case, unless this is 0, the flat connection from the theorem that we have here cannot be used as a representative for the Euler class. And why not? In the case of the Euler class, we were looking at the Pfaffian of the curvature, and we were allowing only metric connections. Metric with respect to some Riemannian metric. Didn't matter which Riemannian metric, but we were only allowing metric connections. So these flat connections cannot be metric with respect to any Riemannian metric. Flat connection cannot be metric with respect to any Riemannian metric on the bundle. because otherwise we could use it as a representative, and then it would follow that the curvature is 0, and therefore the Euler class is 0. Because then, Pfaffian of omega, the Pfaffian of the 0 matrix is 0, and hence the Euler class would be 0. So we really have to be careful here. So this kind of phenomenon cannot happen with Pontryagin classes or Chern classes. If we find any flat connection on a complex bundle or any flat connection on a real vector bundle, then the Pontryagin classes and the Chern classes are trivial, because there we can use any connection. However, here for the Euler class we can use only metric connections with respect to some Riemann metric. So this observation is what makes the theorem interesting. Okay, and I cannot give a full proof of this theorem, but I can give you the idea. And in fact, so we have seen last time that flat connections correspond, or flat bundles with a flat connection, they correspond to representations of the fundamental group. And so let's see what this means in this particular case. The fundamental group of such a surface is well understood. And it's as follows. So the fundamental group of M is the group which is generated by 2G many elements. G is the genus. And let me call them, write it like so, it's generated by 2G elements, alpha 1, alpha beta 1, all the way up to alpha G beta G. So, subject to one relation. So if we did not have any relation, this would mean that the elements here of this group are words in these formal symbols and their inverses. So there would be no relations at all. In particular, they don't commute. It's not a BDM, right? But there is one relation in this case, and the relation is this one, namely alpha 1, beta 1, alpha 1 to the minus 1, beta 1 to the minus 1, and so on, all the way up to alpha G, beta G, alpha G to the minus 1, beta G to the minus 1 is equal to 1. So that's the only relation. And why is that? This follows from a cellular decomposition of the surface. Namely, you can draw a polygon whose sides correspond to these alphas and betas and their inverses. So here we start with alpha 1, beta 1, then alpha 1 to the minus 1, beta 1 to the minus 1, and then alpha 2, beta 2, and so on, all the way up. And the last two things are then alpha G to the minus 1, beta G to the minus 1, which goes this way. If you take this polygon and you identify sides according to where the same elements are identified according to this direction, so you identify this thing with that thing, etc. If you do that, you get exactly a surface which is G. And this is a cellular decomposition of the surface, and so you see these are the generators. So that when you project these elements in the surface, then you get loops which represent elements in the fundamental group, and this one is exactly the same loop as this one up to the direction, And then you have one relation, because if you take the composition of all these loops, then this is filled by a disk and can be retracted. So that gives rise to this one relation that we have. You probably have seen this before. So that's the fundamental group of a surface of genus G. And now what we are actually interested in is homomorphisms from the fundamental group to the structure group of these bundles. And the structure group for these bundles is which one? So in order to get flat bundles here of this type, we need to look at homomorphisms from the fundamental group to which group? GL, sounds good. Then what? Plus, then what? Real, and what else? 2. There we go. Exactly. So we need to look at such homomorphisms. And now, since we know exactly the structure of the fundamental group of the surface, how can we characterize such homomorphisms? So H is characterized by the images of the generators. We call this HA1, which is H of alpha 1, B1, which is H of beta 1, and so on, all the way up to G, which is H of beta G. So those are then elements in this group. So there are 2 by 2 matrices. But it must, of course, satisfy this relation such that A1, B1, A1 to the minus 1, B1 to the minus 1, and so on, AG, BG, AG to the minus 1, BG to the minus 1 is the identity matrix. Right? If you have a homomorphism from the fundamental group to that, you can look at these image matrices, and they must then certainly satisfy this relation. Conversely, if you have such matrices satisfying this relation, this defines a unique homomorphism, because once you the homomorphism, if it's specified on generators, it's specified everywhere. So really, these homomorphisms correspond to a bunch of matrices satisfying this one relation. Okay. So this allows for some explicit computation. And now, we somehow have to relate these to. So if you have such a set of matrices, then we have such a homomorphism, and then we have a flat bundle. And but somehow we have to relate it to the Euler characteristic, right? And how is the relation? And in order to see that, we have to understand a little bit this group. And in fact, so if I'm training that GL plus 2R is diffeomorphic as a manifold, it's not isomorphic as a group, but diffeomorphic as a manifold to SO2 cross something, namely the set of all triangular matrices A, B, C, here, where the diagonal entries are positive. And what is this diffeomorphism? Well, if I have a matrix here, A, then I can write this as a rotation matrix times such a triangular matrix. B, so this is in SO2, and this is in this set. I'm going to give it a name. And why? This is the Gram-Schmidt procedure. Think of the columns in this matrix as basis vectors, R2, so they form a positively oriented basis. If you apply the Gram-Schmidt procedure, you will end up with an orthonormal basis, which gives you an element in here. And how does this Gram-Schmidt procedure work? You take the first column and you rescale it to get it to length 1. So this gives you this first column here, so that's the length of the first vector. You multiply the first vector just by A and do nothing to the other one. And for the second one, you have to subtract some part of the first vector to make it orthogonal, which gives rise to this entry. And then you have to scale it down to length 1, which gives rise to this number, which then is again positive. So this is the map. A mapped to R, comma D, or in the other direction, R, comma D is being mapped to A. So this is this bijective map. It's of course not a group homomorphism, but it's a bijective smooth map. And what this means is that this space here, this is essentially R plus cross R plus cross R. So that is contractible, right? So that's homomorphic to R3. That's contractible. And therefore, GL plus is homotopy equivalent to this space, which of course is just topologically this one. And from this we can read off the fundamental group. So the fundamental group of this GL plus space is the same as the fundamental group of this one, which we know is in set. So that's, in fact, yes. So that's what we see here. All right, and now, if we have such okay, so let's see. So let me look at the universal covering of GL plus, which I denote by GL plus tilde. The universal covering of GL plus. And this is then automatically again a Lie group, because you can lift the multiplication. You can always do that when you pass from a Lie group to its universal covering. You can lift the multiplications up, and you in this way make the universal covering also a Lie group, and in such a way that then it's automatically in such a way that the projection map from the universal covering to the Lie group is a group homomorphism. So what we get is a new Lie group, which is the universal covering of GL plus. And we have this covering map to GL plus. Maybe we'll call this pi at the moment. And so that's your covering map. It's also a Lie group homomorphism. It is certainly surjective. Let me indicate this by this, that the map to the trivial group, and so it's an exact sequence, meaning the kernel is everything, so exactness means that the image of this is everything, so that means the pi is surjective. Of course, for the universal covering is surjective. And now here we have the kernel of this map. So that's a subgroup of this group, which maps to the identity element here. And what's the kernel? Well, we know what the kernel is. The kernel is given by the fundamental group of this space. This is what we discussed last time. So this is actually a principal bundle over that one with fiber, the fundamental group of that space. The fundamental group of that space is isomorphic to Z. So we get a map from Z embedding in here, which is maps to the kernel of pi, so that this whole thing is an exact sequence of Lie groups. So that's the structure. And now suppose we have such a bunch of matrices here satisfying this relation corresponding to a homomorphism 2gl plus. What I can do is I can take all these elements in here and somehow lift them here. Keep this. Maybe one thing I should say before I proceed with this is that this subgroup, so maybe I call this I because it's inclusion, it's injective. That this subgroup I of z in here is actually in the center of this group. Explain. I of z lies in the center of GL plus tilde. So meaning that the elements from this subgroup commute with all elements in that subgroup. That's what it means. And in order to see that, fix some element in K in Z. And I want to show that I of K commutes with all elements in that group, right? That's what I want to show. Now, look at the map that does the following thing. You take an element, let's say little a, so it's a map from GL tilde plus to GL tilde plus. That takes an element in here and maps it to, and now I want to see, what I'm aiming for is I want to check that multiplying this from the left to A is the same as multiplying it from the right to A. I want to check that this is the same as that. So let me take the inverse of this and multiply it. So then I want to check that this always gives me the trivial element. That's what I want to prove, right? All right, good. And now what happens actually if I apply, that's some element in here, if I apply the map pi to it, if I apply the map pi to that, then this gives me pi to k minus 1 and k minus 1. Since that's a group homomorphism, then this will map to 1. This will map to pi of a. This will map, it will map to 1. And this will map to pi of a to the minus 1. So the whole thing will map to 1 to the unit matrix. So, since this maps to the unit matrix, this actually tells me that this element lies in the kernel of this map and therefore in the image of that map. So it's also of the form I of something. So that means I'm not actually ending up in the whole group, I'm ending up in the image of Z. So that's what I proved here. So I can replace this by Z. Good, so I have this map. That's certainly a continuous map. And now this space is discrete. And this space is connected. If I have a continuous map from connected space to discrete map space, it must be constant. Okay, so GL tilde plus is connected. And the target space is discrete. Therefore, we'll call this map phi, let's say, phi is constant. And so that means phi of A is the same thing as phi of the unit element. But if you insert the unit element here, then you get unit element. And therefore, this gives you the unit element for all A, and that's exactly telling you that this thing is the same as that thing, which is exactly telling you that this I of K is in the center of the group. And so that proves the claim. All right, good. Now, okay, we have that. And now what I'm doing, I take, if I have such a homomorphism, I take these matrices, and for each of the matrices I choose a lift to this universal covering group. This can come here now. Now, for A1, B1, all the way up to AG, EG in GL plus, choose corresponding A1 tilde, B1 tilde, all the way up to AG tilde, EG tilde in GL plus tilde, such that they project down to the given ones. And AJ, the tilde is AJ, I of EJ, the tilde is EJ. Okay, and now if I take these lifts and look at the corresponding expression here, that is A1 tilde, B1 tilde, A1 tilde to the minus 1, B1 tilde to the minus 1, and so on. Yes. All the way up to AG tilde to the minus 1, EG tilde to the minus 1. This is now again an element in GL tilde, and it need no longer be equal to 1. Only if I apply pi to it, then I get this expression, which is 1. But this tells me that this expression here lies in the kernel of the map pi, so this is an element in R Z. Right? So that's what it tells me. And in other words, there is a integral number, such that this, to which this corresponds. So there exists k in Z such that this expression here is equal to k. And now I claim that this number k does not depend on the particular choice of lifts. So claim k does not depend on choice of lifts of the particular A tildes and B tildes that I've chosen. And why is that? Well, if you replace, for example, if you replace A1 tilde by another lift, that means that the other lift is of the form A1 tilde times something from this kernel. So it must be of the form I of L times that. Why? If you have another lift, then you can take the inverse of this other lift, multiply to this one, then you get something which, when projected down, gives you 1, and therefore this times the other lift inverse must be of the form I of L. And then you multiply that. So any other lift will be of this form. And if you insert this now in this expression, then, and similarly for the other matrices, if you insert this in this expression, you get this I of L here, and you get its inverse here. But we have seen earlier that these I of somethings are lie in the center, so they can be colluded with all of these elements, therefore they cancel. Right? Okay. Then, yeah, well, A1 tilde I of L. Okay, let's say I replace this by another lift, which I call A1 check, which is then of the form I of L. And then if I do this with A1 check, B1 tilde, check to minus 1, B1 to minus 1, tilde to minus 1, and so on. I have I of L here, tilde, E1 tilde, then I have A1 tilde to the minus 1, I of L minus 1, E1 tilde to minus 1, so on. As I said, I can commute those, and so they cancel. This one cancels. Set. So I have A1 tilde, E1 tilde, A1 tilde to the minus 1, E1 tilde to the minus 1. So the reason why this works is that each element appears once in itself and once in its inverted form. That's the reason why this works. Okay, so if we have, that means if we start with such a bunch of matrices, AJ and BJ, we lift them, we form the corresponding expression that corresponds to the relation here. And it turns out that this is not necessarily trivial, but it's of the form I of k, so there's an integer attached to it. And this integer is independent of how exactly I do the lift. Okay. And now you have to show that this integer is essentially this integer. Up to psi, please. Of this corresponding one. And Milnor shows this using some obstruction theory, which I cannot introduce here now. And so, and once you have that, you can imagine that such a theorem holds. Why? Well, the flat bundles correspond to these systems of matrices, but the number of matrices is determined by the genus of the surface. And the Euler number of the corresponding bundle is given by this lifting procedure. And now you have to check that if you do these lifts, then how far can you get away from the identity? So how big can the deviation from the thing to hold possibly be? You do an estimate, and you show that this estimate depends on the number of matrices that you have here. So you bound sort of term by term, and then since you have G matrices, this K cannot become too large. And it turns out it has actually to be less than this number of matrices, G, if you do the estimate one. And converse, so that shows, if you do that, that shows that if you have a flat connection, then the Euler number must be less than G. Conversely, if the Euler number is less than G, then the K here has to be less than G, and then you have to find such matrices which gives you that exactly K, which is not too far too big, satisfying these relations. Then you have a bundle of that sort. And then this shows that there exists a bundle of Euler number less than G with a flat connection. And the last thing you have to know is that on surfaces, this Euler number here actually determines the bundles up to isomorphism. And then you have the proof statement. So that's the idea of the proof. Okay. But I wanted to show you this construction so that you see what actually has to be done. And for example, there is a particular example where this applies, for those who know that. Mainly, if you look at the spinor bundle, so if you don't know the spinor bundle, don't worry, you can learn about the spinor bundle next term, it's in the spin geometry course. If you do know the spinor bundle, then you know that the spinor bundle, call it sigma over M, that's a complex vector bundle of rank 2, and it decomposes into two one-dimensional complex bundles, sigma plus and sigma minus. This always happens in even dimensions, in particular in 2 dimensions. And so this is a one-dimensional complex bundle, so it's complex line bundles. And so in particular they are, from a real perspective, plain two-dimensional bundles which carry an orientation induced by the complex structure. And if you take these bundles, they are dual to one another, then it turns out that the Euler number for these bundles, when integrated over the surface, gives you plus or minus 1 minus g. So the modulus is less than g, and so the theorem applies. So these bundles do have flat connections. These connections cannot be metric, of course, but they can also not be complex. So when you consider this as a complex bundle, there's no flat connection, you can show that. But if you consider it as a two-dimensional real bundle, then there is one. So it's quite subtle. And it would be nice to write down such a connection explicitly in this particular case. All right, so that's a warning. So the Euler class is really different in many respects from Pontryagin and Chern classes. And we have seen this earlier. The Euler number is not a cobordism invariant, for example. And here we also see that the non-trivial Euler class does not imply the non-existence of flat connections. It only implies the non-existence of metric flat connections. Okay. Questions about this? Good. Then let's move on and recall something, namely when we discussed the characteristic classes in general. So what we did, recall. So we started with an invariant polynomial for Lie group G, and this Lie group used to be either GLNC for complex vector bundles, GLNR for real vector bundles, or SON for oriented Riemann vector bundles. And so we started with such a polynomial. And when we discussed the independence of the characteristic class of the connection, what we did is we looked at two different connections, number 0 and number 1, on a bundle, connections on vector bundle F over M, the structure group G. And we wanted to see that if I insert the curvature for the first connection, for one of the connection, minus the curvature of the other connection, that these two differential forms are not equal, but the cohomology class is equal. So that means the difference must be exact. And in fact, we showed that this is the differential of a particular form of 1 degree less, which was called the transgression form. And we want to make use of this now in the situation when we have a flat connection on our bundle, so that Pontryagin classes and so on are 0, but we can use the flat connection maybe as a reference connection, and then obtain, by looking at this correction term, obtain an invariant for the other connection, number 1, which may not be flat. So that's what we want to use. So now we want to look at a situation where the Pontryagin classes, for instance, are 0 and are non-interesting, for example, on a flat bundle. But nevertheless, this correction term may be of interest if we use a flat connection as a reference connection and give us some information about the other connection. So that's the idea now. So we come back to this transgression form now. All right. So how did this transgression form look? Let's recall that too. So this transgression form, which was associated with a pair of connections, was of the form: take this polynomial and apply it to the curvature of omega hat of a connection. Yeah, omega hat of connection nabla hat. Where nabla hat was a connection not on the manifold itself, but on the cylinder over the manifold. And it came about by interpolating the two connections, number 0 and number 1. More precisely, we first pull back the two connections from M to the cylinder on the pullback bundle over the cylinder, and then we took the linear interpolation between them. So this looks like this: 1 minus t number. Oh, this is 0. It should be 1 plus t. No, it should be 0. Plus t times number 1 hat, where number 0 hat and number 1 hat are the pullbacks of number 0 and number 1 to the cylinder. So that's what we did. Alright, so then we can form this differential form over the cylinder. But now this gives us a differential form on the cylinder, but here we want a differential form on the original manifold, of course. And so we applied this operator Q to it, this homotopy operator on differential forms, which was defined as Q applied to some form eta. Eta is a form on the cylinder, and applying Q to it gives us a form on the original manifold M, but of 1 degree less. And it should be of 1 degree less because we apply d to it, so then we get back to the original degree of these forms, right? And the formula for this homotopy operator was to take the integral from 0 to 1 of this form eta, to which we apply it, and there we insert, well, that's on the cylinder, we insert the dt direction here along this 0-1 interval, and then we take the differentials of the t of x1 up to the jt of xk, so those, and integrate over t. So remember with jt, we have two things here. We have the projection I from the cylinder to the original manifold. And so that's the map along which we pull back the bundle and the connections to get to this connection. But we can also go in the other way. For each t, we have a map from M to the cylinder by mapping x to x1t. So we slice in that is. And that's what I'm using here. Alright, so that was the formula that we proved. And in particular, this told us that these two forms are homologous and therefore represent the same homology class. And we also computed this term here, or term here, namely, we found that for this, so you can compute the omega hat for this particular interpolation and put everything in this formula, and then what we found was that this is equal to 1 on k is the degree, integral from 0 to 1 to mu of omega 0 minus omega 1 or omega t, omega t dt, where mu is related to the polynomial p by polarization. So p of x is mu of axis. And so we obtain that's a symmetric multilinear form, which we obtain by polarization from P. And yeah, that's the formula. All right. Good. K is the degree of eta, or here. All right, and now let's evaluate this whole thing in case that we have a flat reference connection. Now assume that number 1 is flat. So that means omega 1 is the zero matrix. Then in order to evaluate this, I have to see what I get for omega t then. Omega t was also an interpolation of the curvature matrices. Is 1 minus t omega 0 plus t omega 1. And then there's a correction term of lower order, which is quadratic. And we get the difference of the two connections squared. So that's what we obtain. We have all computed all of that. So we know all that. And if the thing is flat, then of course this term can be discarded. Now what you can do is you can put this omega t, this is formula, in that formula, and the t dependence is rather simple because it's just given by these prefactors, and they can be pulled out of this multilinear form and integrated out, so that we get rid of this integral. So let's do this in an example at least. Namely, the example that we are dealing with the first country alpha class. In this case, the polynomial that we need to evaluate on the curvature is quadratic, and we have computed it, namely we have this prefactor minus 1 pi squared, and then we have to take the trace of the matrices. So that's a polynomial that gives rise to the first country alpha class. That's something we have explicitly proven a few weeks ago. And now, alright, so if we polarize, then we get a symmetric bilinear form, and we can, of course, directly read this off from the formula. So what symmetric bilinear form do I have to take in order to get, when I put y equal to x, I get back this expression? It's clearly the trace of x times y. And this is symmetric. The trace of x times y is symmetric in x and y. So that's the mu that we need to insert in the formula. So in this case, it's relatively simple. So our transgression form, and the theorem number 1, well, I'm now assuming that, I will be assuming that number 1 is flat. So this is mu of p omega hat, and this is given by that formula. Now, what is the degree in this case? This 1 on k term. Well, the whole thing is a form of degree 4. So here we have which equals 3 1/3. Then the integral 0 to 1 u omega 0 so 1, comma, and now I have in the other slot, there's only one other slot, I have to insert the formula of omega t. Is this formula, the omega 1 term is not there. So we have 1 minus t omega 0 plus t 1 minus t, and then the square of the difference of the two connection forms dt. Alright. Now the mu is explicitly given by this, so I have minus 3 times 8 is equal to 24 pi squared, and then I have two terms here. Okay, these long integral, so this is linear in the second slot. So I have the trace of this one. So here I have the trace of this one times the other one, which is this one. So, on the right side. Okay, so we have two terms, one with containing the curvature here. So this gives me trace of that term. Then I have to integrate 1 minus t from 0 to 1, which gives me 1/2. Integral gives me 1/2. Then I have 1 t from 0 to 1 wedge curvature. So that's what we have in this part. And here I have to integrate t times 1 minus t from 0 to 1. Yeah, that's t squared minus t cubed. T squared integrated gives 1/2. T cubed integrated gives 1/3. 1/2 minus 1/3 is 1/6. And I have here the trace of omega 0 minus omega 1 to the third power. Right. And now, in order to simplify this further, we can assume that we choose our frame with respect to which we do the computation by parallel sections. Because remember, the connection nabla 1 is parallel, it is flat. It is flat. And if you have zero curvature, you find locally parallel basis fields. You just take a basis at one point, and then you do parallel translation in radial directions. This gives you a local frame. And this frame is parallel, so also if you differentiate in any other direction, it gives you 0, because the curvature is 0. So it's essentially what we did last time. So now I make a further restriction, namely assume that the local frame with respect to which we are doing the computation is parallel. So here, now assume that local frame is parallel with respect to the flat connection, which is number 1. And then the omega 1 is also 0. The middle omega 1. So then, let's see how things simplify. Trace. So then we get 1/2 of omega 0, which omega 0 plus 1/6 omega 0 cubed. Alright, and now we recall the structural equations, which tell us how we can compute the curvature out of the connection, namely omega 0 is d of little omega 0 minus omega 0 squared. So let's insert this. Then we get 1/2, or maybe I pull the 1/2 out, then I have 48 here. And I can drop the 1/2 here. And I have little omega wedge d little omega minus little omega squared plus 1/3 omega cubed. Which is minus 1 on 48 pi squared trace of, here I have little omega, which d omega, then I have minus 1 omega cubed plus 1/3 omega cubed, which gives me minus 2/3 of omega cubed. And maybe you have seen this before. At least the physicists in this room may have seen this before. If you call omega 0 a, then you have perhaps seen it. Now then you have a wedge dA minus 2/3 a wedge a. You have seen it this way. Oh. It's called the Chern-Simons fault. Good. And in particular, that's of interest for three manifolds. If you are on a three manifold and you look at the tangent bundle, then of course the Pontryagin class, which is of degree 4, will be vanishing anyway. And that will certainly not give you anything interesting. And all these classes are, if you apply them to the tangent bundle, are of interest only on odd and even dimensional manifolds. However, that's a three form, so that on the three manifold we might want to integrate this over the manifold and get something interesting out of that. If we apply this to the tangent bundle, then of course in order for this to carry this out, we need a flat reference connection. And in the case of three manifolds, or rather orientable three manifolds, we actually always have flat connections on a tangent bundle because the tangent bundle turns out to be trivial. Always on oriented three manifolds. That's a peculiarity of three-dimensional manifolds. And so that's the next thing I want to explain. So that we will be able to apply this construction to three manifolds. And this proof that shows that three manifolds are always parallelizable, always parallelizable, then that proof is actually quite interesting because it demonstrates the method of obstruction theory. So that it's worthwhile looking at that anyway. So how does this go? So in fact what I want to show is position. Well, if I look at the tangent bundle, I can equip it with a Riemannian metric and look at the corresponding orthonormal frames. In the oriented case, this will then give me an SO3 bundle. And there are two steps to be done. The first thing is to lift this SO3 bundle to the universal covering of SO3, which is called spin 3, similar to what we did in the Milnor theorem, except that in this case it's not a Z covering, it's just a Z modulo 2 covering, it's a double covering. And then, once you know that you can do that, your frame bundle can be replaced by a spin 3 bundle. Group spin 3, by the way, is the same group as SU2, which you may be more familiar with. So, and then we show that this spin 3 bundle must be trivial. And let's do that. So, on any spin 3 bundle, principal bundle, on a three-dimensional manifold, So we will apply this, let me just recall it, to the tangent bundle. We will start with the tangent bundle, okay, with the Riemann metric. Then we have a frame bundle for that, which is an SO3 bundle. We will lift this to the spin 3 bundle. Let me see the spin 3 bundle is trivial. Then the SO3 bundle that we started with is trivial, and then the tangent bundle is trivial. So that's the logic. But let's do this now. Okay. Proof. Now this group. So what is actually, so spin 3, so by definition basically, is the universal covering of SO3. And so what is it as a manifold? As I said, in fact, this is isomorphic to SU2. And you can write down the covering map also as a map. So if you don't want to work with the abstract covering space, you can do it concretely by writing down, in fact, twofold covering map from this group to that group, if you want. This is how it's typically done in physics books. And anyway, so what is of interest to us now only is the topological type of this group. So does anyone know what manifold SO3 is? RP3, exactly. So spin 3, so the universal covering of the RP3 is the 3 sphere. So that is diffeomorphic to F3. And so in particular, this tells us something about the fundamental groups of this group. So spin 3 is connected. So pi 0 is trivial. And S3 is also simply connected. So pi 1 is also 0. It's also trivial. It's lucky here. Just write this. Now, how about pi 2? Second homotopy group. And in order to find what the second homotopy group is, you could apply the so-called Hurwitz theorem, which tells you that it actually must be isomorphic to the second homology. The Hurwitz theorem, if you don't know the Hurwitz theorem, don't worry, you will learn this in the algebraic topology course next year. And the Hurwitz theorem tells you that if you have a space such that m pi 0 of the space all the way up to pi k minus 1 of the space, so that all 0, then it follows that on the next level, the map from pi k of m to hk of m, into the coefficients, as a natural map, that this is an isomorphism. And now the homology groups of the spheres can easily be computed. And if you do this for this 3 sphere, you get 0 here. So the Hurwitz theorem tells you that the map from pi 2 to h2 is an isomorphism, so therefore the pi 2 must also be trivial. And then you can apply the Hurwitz again for pi 3. Right? And you get that pi 3 is isomorphic to h3 of S3, which is Z. So you know the third fundamental group. And then you cannot apply the Hurwitz theorem anymore because you don't have this requirement. But anyway, so it turns out that the second homotopy group is also trivial. Okay, so the group is connected, simply connected, actually also two connected. This group spin 3. That's important for the argument to follow. How can I show that a principal bundle is trivial? A principal bundle is actually trivial if and only if it has a global section. And so we need to construct a global section. Of our principal bundle. Of the principal bundle. And in order to do that, a global smooth section or a global continuous section, doesn't really matter. once you have a global continuous section, you can also smooth it and get a global smooth section. So I will construct a global continuous section. Okay. And yeah, how can we do that? Well, I go ahead and choose a triangulation of the manifold. Triangulate M. And then we have decomposed our manifold into simplices, 0 simplices, 1 simplices, the edges, 2 simplices, and so on, and then 2 simplices and 3 simplices. And well, and what I'm doing is I'm constructing this global section on first the 0 skeleton, which is just the vertices. Then on the 1 skeleton, which is when I add all 1 simplices, then I extend it to the 2 skeleton when I insert all faces, and finally I extend it also to the 3-dimensional parts. I go, I do this level by level. Okay, so let's say for each 0 simplex, well, that's easy, right? The 0 simplices just form a discrete subset of the manifold. And to construct a section there is no big deal. You just pick one element in the corresponding fiber. For each 0 simplex, sigma 0, choose. So let me call this section S. Choose S of sigma 0 in the corresponding fiber. In some way, doesn't matter how. So that's easy. Now I extend it to the 1 skeleton. So for each 1 simplex, sigma 1, which is just a line, compact line, ending at 2 simplices. I have now the situation, so here's my 1 simplex, and the endpoints are 2 vertices, 2 0 simplices, and on the endpoints I have chosen some elements in the total space, so the corresponding fibers. And what I need to do is I need to connect them in a continuous fashion along this curve. And in order to do that, I can certainly trivialize my bundle over this 1 simplex. All simplices are contractible, so our bundle can always be trivialized over any simplex. So trivialize the bundle over sigma 1, and then along sigma 1, my bundle is trivial, so the sections in this bundle just correspond to maps from this line to the fiber, which is spin 3. So section correspond to maps from sigma 1 to the fiber, which is S3. So what's the situation now? So we have this basically interval, and we have a map which is specified at the endpoints, because there we have already chosen our thing. So this this endpoint is getting mapped to one point in S3 and that one also, after applying utilization. And we have to extend, and we can do that because S3 is connected. So can continuously extend the section to sigma 1 because S3 is connected. This we do with every one simplex. Next, we want to extend it to two simplices. So we have extended our section to the one skeleton, the union of all one simplices, and now we extend to the next one. For each two simplex, sigma 2, again we trivialize bundle and contractible. And now we have two simplex, sigma 2. We have three boundary components which are one simplices, and now the corresponding map from sigma 2, our section corresponds now to a map from sigma 2 to S3, which is S3. And we have already defined it on the one simplices, so we have already defined it on the boundary of these two simplex. And we need to extend it in a continuous fashion to the interior of the two simplex. But now we use that this S3 is simply connected, which means if your disk defines a loop in S3, and since the manifold is simply connected, we can contract it and to a constant loop. And this is the same thing as saying this continuous map can be continuously extended to the interior, because this will give you the contraction to a constant path. So since S3 is simply connected, we can extend the section S to continuously to the interior of sigma 2. This we do with every two simplex, and so we have then a continuous extension to the two skeleton of our manifold. And the last step is now obvious, right? Now we have to fill in these three simplices. So for each three simplex, we do the same thing, trivialize, bundle, that's 3, and then we have already the section is already defined on the boundary. The boundary is homeomorphic to a two-sphere. So we have a continuous map from the two-sphere into S3, and we want to extend it to the interior in a continuous fashion. And for this, we use that pi 2 is 0. Okay, so since pi 2 of S3 is trivial, S can be extended continuously to the interior of the three simplex. And this way we do this with every three simplex, and this way we have found a continuous section of our principal bundle of the whole three manifolds. And that concludes the proof. You see, this would not work if we tried to do this within three principal bundles on four-dimensional manifolds, because then we would have to go one step further. We would have to take four simplices and extend, but then we would have a three-ball mapped into S3, and we would have to extend this to the interior, which we cannot in general do because pi 3 of S3 is not true. In that sense, these fundamental groups set up obstructions to this extension procedure. But in this particular case, it works fine. And so I thought this is really nice to see, and that's why I demonstrated how this works. Good. So you always hit with these V groups. You always hit an obstacle at pi 3. Yeah, and also the conclusion would not be true. Right? So I mean, for example, on S4, that's oriented and spin, but its tangent bundle is not trivial. Okay. Yeah, the obstruction lies at pi 3. Okay, so once we know that each oriented 3-manifold is spinnable, and that means that the SO3 frame bundle of the tangent bundle actually lifts to a spin 3 bundle. Then we know by this proposition that this spin 3 bundle is trivial, and therefore the tangent bundle is associated with this is an associated bundle to the spin 3 bundle, because you just take the map from spin 3 to SO3, and then you take the standard representation. So then you get back your tangent bundle. So if the principal bundle is trivial, then the corresponding vector bundle, associated vector bundle is also trivial. So that means then it follows that Tm is trivial. So the spinnable condition, unfortunately, if you want to discuss this in an elegant manner, you need the Stiefel-Eakin classes, which take value since at module 2 and which I haven't introduced. So I have to give this. All right, and so from that, then it follows that each orientable 3-manifold is parallelizable. So that's the plan follows. Of course, non-orientable 3-manifolds are not parallelizable. I mean, if the tangent bundle is trivial, then the form bundle is also trivial, and that means the manifold carries no rotation. So it's actually an equivalent, right? Orientability and parallelizability in 3 dimensions. And also note that I did not assume that the manifold is compact here. That's not of relevance. It can be any 3-manifold. You just need this triangulation, and then in the non-compact case, you have infinitely many vertices in each dimension, but this doesn't matter. This procedure can be carried out anyway. So this also, in the literature, very often it's stated only for compact manifolds, but actually compactness is not relevant here. In 4 dimensions, so if you have an SO4 bundle, and you can lift it to the spin 4, and that's the universal covering, so you cannot lift it any further than that. And then it still does not follow that the bundle is trivial. And and the 4th sphere is an example. So unfortunately, it's not like what you suggest. So this is really a peculiar fact about 3-manifolds. Yes, but it cannot be more connected than spin. Spin is simply connected, and it cannot be more connected than spin because it's the universal covering. There's nothing above that. But they are not for Lie groups. It just doesn't happen. So pi 3 is non-trivial. But in 3 dimensions, that's not a problem for us. In high dimensions, it is. Yes. Of course, if you can reduce your structure group, so it's not by passing to a covering, but by passing to a subgroup. And if you reduce your frame bundle, you can reduce it to a subgroup, for example, a trivial subgroup, then everything is trivial. But that's a tautological statement, basically. But using coverings, this is the best one can do. All right. Any further questions? Doesn't seem to be the case, so then we are 5 minutes early today, something like that.